Howdy everyone. Today we're going to do some simple tests down in the bat cave. I've pulled out some test equipment. Nothing really elaborate, just a couple of voltmeters. We've got the one on the right that's going to be measuring current, and the one on the left is set up to measure voltage. And our subject is going to be the 16 LED fixtures. This one was mounted on the tractor and it was causing all the RFI, knocked out the AM FM radio completely. So I thought I would bring it in, do some experimenting on it, throw a little science at it, and see if we can illustrate what's going on. So don't get too confused by the wiring here. All we're basically doing, I've got a power supply up on top here, and it's an adjustable supply and lets me vary the voltage from 0 volts up to what we need to properly drive the LED fixture here. And on the right side meter there, it'll also display the current that the power supply is delivering to the load. In this case it's going to be that lamp assembly. What I've done also is I've taken the output of that power supply and I've connected it up to an oscilloscope here. And what we're going to do is, right now I'm just monitoring the DC voltage, and it's pretty much going to mimic what we see on this left meter here. So let's go ahead, and you'll have to forgive me, this power supply is a little bit noisy. Right there you can see we've got it adjusted roughly for a little over 7. You can see, for example, right there, this is my 0 volt reference. We've got it set up here so that there's 5 volts per division, which means here's 0 volts, here's 5 volts, 10 volts, 15 volts. So that's the way this thing is set up as far as sensitivity goes. So when we fire up the power supply, you can see right there it immediately jumps up 5 volts, 6 volts, yeah, 6.5 to 7 volts, and that's what's showing up here. So as you can see, at roughly 6.5 to 7 volts, we're not drawing any current on the other fluke meter, and sure enough no LEDs have come on. Now what I'm going to do is I'm going to very slowly start increasing the voltage on the power supply, and I'll try to read off the levels right here. I'll be reading off the levels on this fluke meter right here. I want you to pay attention to what happens here to the LED display. So I'm slowly increasing. There's about 6.7, 6.8, 6.9. There's 7.5 volts, and right about there, just under 8 volts, and the LEDs do in fact start coming on. So still not drawing much current. Let's keep, and pretty much confirmed by the current meter on the power supply also. So at this point the LEDs are just barely being tickled at about 8 volts. So let's keep cranking up the voltage. There's about 8 volts. Right there we're starting to draw a little bit of current. That's an awfully low amount of current. That's actually about 10 milliamps of current. It's hardly anything, and yet the LEDs are already starting to be pretty bright. That's at about 8.3 volts. Let's keep going. So there's 8.5. You can see the current meter is rising. LEDs are getting brighter and brighter. Back off so that you can get a better view. There's about 9 volts. LEDs are getting definitely brighter. Current meter, you can see right there, we're already at 0.12 amps. That's 120 milliamps of current. That's at about 9.2 volts. LEDs are pretty bright at this point. Let's keep going up. Alright, there's about 10 volts right there. So we've got 10 volts. We're drawing just under 0.4 of an amp of current, and the LEDs are really bright. We're really lighting up the workbench here. Let's keep going. There's 10 volts. Current's rising. We're up to 600 milliamps right now at 10.4 volts. Let's keep going up. Okay, there's 11 volts. At 11 volts, we're drawing exactly 1 amp of current. Shows you how efficient the LED light fixture is. You'll notice something that we're going to come back to in just a little bit. You can see that the DC level has risen just over 10 volts. We're at about 11 something volts. But you'll notice that there's a lot of noise up on top of that DC level. And this actually is the source of our RFI. And we're going to come back to that in just a little bit. So let's keep going. We're at 11 volts and about 1 amp. There's 11.4 volts, 11.5. Right now we're drawing about 1.46 amps, 1.47. So just under 12 volts, 11.7 volts. We're just under 1.5 amps. Now what's interesting is from this point on, notice I'm at 11.8 volts, and notice what happens to the current that I'm actually drawing. Pay attention to these 2 meters. I'm going to keep upping the voltage. I'm now at 12 volts, and the current is actually going down ever so slightly. So right now we're at 12.5 volts, 12.6 volts. The amount of current actually has gone down, and that's because of the switch mode power supply that's inside here. It's doing its thing. The input supply voltage is getting higher and higher, and it's making sure that the LEDs don't get burnt out. Let's keep going here. There's 13 volts. We're drawing 1.3 amps. There's 13.8 volts. We're down to 1.2 amps. There's 14 volts. We're at 1.2 amps. LED brightness has not changed all this time. It's been pretty bright. And we can crank this up even higher. There's 15 volts, for example. And we're down to 1.3 amps. The LEDs are very, very bright. So you can see, get an idea. So the 1.3, or actually at this point, 1.13 amps is coinciding with what the power supply meter is showing just over 1 amp of current. But note what is happening here. This straight line, this should be an absolute straight line if this were pure DC signal. And it is coming from the power supply. But what's happening is the switch mode power supply inside this light fixture is generating so much RF hash, so much radio frequency interference. What's happening is the noise from that power supply is coming back out onto the power leads, and even though we're directly connected up to that power supply, the oscilloscope is monitoring that voltage and it's letting us see what's actually going on. And you can see there's a tremendous amount of noise on that DC voltage that we're running right now at about 15 volts. So let's turn that down a little bit. Yeah, we can bring that down to, typically, let's say 13.8 volts. That's typically what most alternators run at. This is what you would about run on your tractor and things like that. Current's at about 1.25 amps. So there you go, 16 LED lamps. Don't pay any attention to what they tell you as far as the wattage of the unit. I've seen all kinds of stupid values for the wattage of these units. If you want the real wattage, take these two numbers, take 1.22, multiply it by 13.8, and that will be the input power, the power that's being consumed by this LED fixture. Okay, now I'm going to go ahead and readjust the oscilloscope so that we can get a closer look at this fuzz, at this noise that's going on, because this is the source of the issue. This is what's knocking out that AM/FM radio. And then also we've got a different instrument. This is a spectrum analyzer, So this instrument lets us look at the waveforms in the time domain. In other words, we get to look at how strong the signal is. So that's the amplitude on the y-axis here, and then along the x-axis here we're looking at time. So that's along the x-axis. This instrument here is going to analyze, we're going to hook up this signal up to it, and it's going to analyze the signal in the frequency domain. In other words, we're going to look at the amplitude on the y-axis here, but along the y-axis, but along the x-axis, we're going to be looking at frequency. So we're going to be comparing the amplitude versus frequency, and we're going to learn a lot of very, very interesting things when we hook up the signal to this spectrum analyzer, and we'll see why it totally knocked out the AM/FM radio. All right, so let me first adjust this guy here and show you something interesting. Alright, so LED fixture is still on. I've gone ahead and turned off the fluke meters to save their batteries, but they're still monitoring voltage and current if we wanted them to. We've got the meters up on the power supply verifying they're still on. I'm running it at 13.8 volts, exactly how we left it. And what I've done is I've adjusted the oscilloscope here now. I've gone ahead and AC coupled the signal so that the DC signal is going to be pretty much in the center here, and I've increased the sensitivity a little bit, and this is actually pretty shocking, the results that we're seeing, and this absolutely explains why this LED light fixture is totally knocking out the radio. So we can see right here we've got regular pulses, squirrel wave pulses from the switch mode power supply, and it is dirty as sin. This is about as nasty of a signal as I've ever seen, and I've seen a lot of them in my engineering career, but this is about the worst I've ever seen. So it's pretty simple with these oscilloscopes. I set it up here to read out for us the frequency of this signal. The fundamental frequency is just under half a megahertz, roughly about 476 or so, 475, 476 kilohertz, and get a load of the peak-to-peak value. Just under 1.6 volts peak to peak is the noise being generated. So put it in perspective, we got a 12 volt signal from your tractor, battery, alternator, whatever, let's call it 13.8 volts, coming down, and it's feeding this LED light fixture. The light fixture, because of its very, very poorly designed switch mode power supply, the Asian manufacturers managed to save themselves about $3 or $4 worth of cheap capacitors and inductors. All they had to do was put in about 3 or 4 parts in here, and they could have filtered the noise that's being generated by this thing, but instead they didn't. They saved themselves a few bucks. That noise then comes back out onto the power lines, which we're measuring. So out of the 13.8 volts that we're putting in, that power supply, or the switch mode power supply, is spitting out 1.6 volts of noise, peak-to-peak noise. That's absolutely horrible. I can't tell you how bad that is. That's like as the worst I've ever seen. So pretty much confirms what we've suspected. And just for the heck of it, let's go ahead and look at that signal on the spectrum analyzer. Well, let's see. I see all kinds of fundamental. I see a fundamental frequency of just under half a megahertz. But you know what? This signal is ringing. I'm a little bit too close, zoomed in too much. It's not able to focus. But this signal has got so many. It's ringing so bad that it's generating harmonics all over the place. So along with the half megahertz signal, I'll bet you we're generating harmonics well up into the HF and probably the VHF range, which means, you know, right up from the AM radio band up to the FM radio band, and maybe even beyond that. So let's see if we can get a confirmation of that by putting it onto the spectrum analyzer. Alright, so now we've got, instead of signal going to the oscilloscope, what I've done is I've coupled it over to the spectrum analyzer. The exact same setup. The only thing I've done is I've added in a small device here to protect the spectrum analyzer from any DC voltages. These instruments are very sensitive, and I could actually damage it if I were to apply too much of a DC voltage from the power supply into it. So this little device here lets the RF signal pass through, but will block the DC component. So here, what I've done is I've set up spectrum analyzer to sweep from very, very low frequencies, from well down below the AM band. Here you can see right in the middle is about 100 megahertz. And these are FM stations that are being picked up by my loose wires here. So these wires here are acting as an antenna, and the spectrum analyzer is acting like a receiver, and you can see we're actually picking up some FM stations. So that's, let's just call it 0 hertz. This is about 100 megahertz, and this is 200 megahertz. So a total span of 200 megahertz, and we're looking at about 20 megahertz per vertical division here. So this, let's call that 0. That's 20 megahertz, 40, 60, 80, 100, 120, 140, 160, 180, and there's 200 megahertz. And this is our baseline. So let's go ahead and turn on the power supply, and let's see if this LED light fixture generates any RF noise. Let me reach over here, we'll flip the switch, and there's our answer. It's like holy cockaballs. That's really, really, really bad. That is about as much noise as you couldn't make a noise generator better than this device here. If you wanted to make a device to generate all kinds of hash, trash, and noise from extremely low frequencies, wipe out everything AM radio band, FM radio band, all the way up to several hundred megahertz. That's what that little power supply inside there is doing. So this is why, this is the signal that was conducted onto the power line from that power supply. We're actually monitoring the RF signal on that power line. You can see just how severe the RFI is, the interference. Let me see if I can zoom in a little bit, get a little more definition on the signal, but this right here answers all of my questions. Extremely, extremely strong signals and extremely broadband. Tells me there's absolutely zero filtering put inside that LED fixture. Alright, so what I've done is I've adjusted the span of the spectrum analyzer to go from close to 0 hertz. This time only up to about 5 megahertz. So the total span is only 5 megahertz wide. And we're still looking at the same relative amplitude scale. What I've done is I've set up 2 markers. I've put a marker here. I hope this stays in focus. There we go. So I've set up one red dot here on top of this pulse. And then we take a look at the very, very next pulse. I put a marker there. And the spectrum analyzer can give us the difference between these 2 frequencies. And it's reading about 473 kilohertz. That agrees very, very closely to what we were measuring on the oscilloscope when it was telling us about 475, 476. But I would absolutely trust spectrum analyzer way, way more, because that's what this guy's job is. It's able to define frequencies and amplitudes extremely well. So this is really horrendous. This is such a noisemaker that it's unreal. To those that are in the EMI, EMC community, you've seen stuff like this before, but to those not familiar with what's going on here, just trust me, this is about as bad as it gets. Okay, so I just realized there is a lot better and easier way to define what the fundamental frequency of the oscillator that's inside that light fixture is. I went ahead and set up the span to go from 0 to 2 megahertz, and I just had it read the frequency directly of the first pulse. And in this case, the primary frequency of the fundamental is right at 477.333. So there you go. That's the frequency of the oscillator that's inside there. And if I set up a marker over here, that difference should be very, very close to 477. Let's see, just for the fun of it, what happens. Alright, wrap this thing up. I went ahead and adjusted this to do a delta function. We've got a lot better resolution now, and I've set up 2 markers and had it measure the delta between them, and sure enough it coincides exactly to the fundamental frequency that we measured earlier, that being 477.3 kilohertz. So the next step will be to design and implement a filter to put right before the power lines here on this light assembly, so that all the RF noise and hash that this piece of junk is generating does not get back on the power line and contaminate all the electronics in the tractor. Alright, let me go ahead and get this posted, and if you have any questions or comments, please don't hesitate to ask. And if you like the video, please give us a thumbs up, and by all means subscribe if you like this kind of stuff. Thanks, we'll see you later.